Hey, everybody. I wanted to take a minute and recap what we did today, and I thought I would do it a little bit differently because I'm kind of tired of the screencasting with the, little whiteboard, and I thought this would be more fun. And I think you could see pretty well on this board here in this room. So I wanted to recap what we did about electric field because I know I presented it to you in a way that's a little bit different than you might see in your book, but I really do think it's a much more intuitive way to approach how to calculate electric potential energies. I wanted to remind you why we're doing this, right? So we have electric fields. We know a lot about them. We've gotten really good at, analyzing them and calculating them. And that provides one window into how to analyze how charges behave in space, right? Just like forces in F equals ma provided a window for us to analyze the motion of a charge. What we saw was that sometimes it got really complicated, especially if the path you were taking got curvy or there was a lot going on. It got kind of hard to figure out the acceleration at every point and how the force was acting at every point. And that became just a complicated situation. And so we realized that we have another formalism at our disposal, which was the idea of energy, so that we can, instead of looking at like how a force acts every single step of the way along a particle's motion, we could say, well, all right, well, we don't really care in a lot of cases how the particle got from point A to point B. We know in the case of conservative forces like gravity and springs and the electrical force, it turns out, really doesn't matter how I get from point A to point B. It just matters that I'm at point A and then I'm at point B. And so instead of talking about how forces behave along particular paths, we can look at work done and energy transformations and say things like, well, instead of saying there's a force that acts to accelerate this charge from here all the way to over here, I can say, well, I know energy is conserved, so the potential energy it had here becomes kinetic energy down there. And I could accomplish the same goal in a much simpler way. Moving from forces to energy doesn't always work. Sometimes you really need to go down to forces, but energies allow you to analyze befores and afters rather than in betweens. And it's a great formalism. Physicists love energy because it often simplifies some very complicated problems. We want to move now from forces, which were electric fields and forces, to potentials and potential energies, which are going to allow us to take an energy treatment of electric force and ask the question, not what's the force acting on these particles as they move around in space, but what are the energy transformations at play as these particles move around in space? The other thing I want to talk about is like, what does it even mean for a charge to have potential energy, right? Like if you think about that, why should a charge have potential energy? If I'm in empty space and I put a little charge down, it doesn't have any potential energy because there's nothing else around it. So it's like being on flat ground, right? There's nothing there to give it any potential energy. So a charge has potential energy, and this is important to remind yourself, when it's in an electric field that is caused by the presence of other charges. So let me say that again. A charge has potential energy when it's at a location in an electric field, right, in the presence of other charges. Because to get it there took some work. To get it out of there is going to take some work. Whenever it takes work to get something in or out of a spot, usually it has potential energy, except in the case of something like friction. Okay, so let's take a look at forces and think, well, how do we move from forces to energy? So you remember we talked about this little equation, force equals EQ, where E is the electric field, force is the electric force. This electric field is created by some distribution of charges, not Q. Oops, not Q. Q is placed in that electric field, and then it now feels a force by the electric field caused by something else. We defined electric field this way as if I have a charge Q at a point where there's an electric field, and I know that charge Q feels a force F. If I take the amount of force that charge feels and divide by the amount of force that it actually feels, it allows me to talk about the electric field at that point in space at some point. And what's cool about that is it kind of takes what's sitting there out of the equation, literally. And so I can say, well, okay, I don't really care, like that this particular charge feels this amount of force. I care more importantly, what is the force field in space and how would it affect things that come into that field? That's what electric field allows us to do. And remember, it had units of newtons per coulomb because it's talking about the force per unit charge felt at a point in space. Okay. Similarly, I can come along and I can talk about the potential energy of a charge at a point. So if I have a point, I can say the potential energy of a charge at some point P And remember, charges don't just have electrical potential energy unless they're near other charges. You have to be near another charge for that to happen. It's going to be equal to the charge Q times some sort of thing we'll call potential at that point P. And so if I know, just like if I know the charge and the electric field, if I multiply them, I can get how much force the field exerts on the charge. If I know the charge and I know the potential at that point in space, and I multiply them, I can get how much potential energy that charge Q has at that point in space. Okay, and we can see, again, I can do the same thing here. U of P divided by Q equals V of P. And you can see then that V of P has units of joules per coulomb, which is the volts, named after Alessandro Volta. Okay, so those are two cool things. I've defined this idea of electric potential, and this might seem weird, but it's not if you think of it this way. Like I walk around life and I can say something like, you see that hill over there? That's a really high hill. There's another hill that has a low hill. And I can talk about how much potential energy either of those hills would give to something without putting anything on the hills. I know that the higher hill has a higher potential, the lower hill has a lower potential, and I can discuss the hills, which is really the important part. And no matter what I put on top of them, the higher hill is going to give the thing more potential energy. The lower hill is going to give the same thing less potential energy. V allows us to do the same thing about electrical terrain. And let's say, okay, that point over there, V, is going to give a certain amount of energy to a positive charge were I to put it there. I know that point's at a higher potential than that point, which would give less energy to a positive charge were I to put it there. And that's one important thing is potential, that there's sort of magnitude of potential is defined as the amount of joules, the amount of potential energy a positive test charge would have at a given point in space. Just like electric field is defined as the amount of force that would be felt by a positive test charge at that point in space. Okay, so that's all good, but like, how do you actually really make sense of potential energy and potential? How do I actually calculate these things, right? Like electric field, we said we could do a lot of calculus and get electric fields. How do we actually, and it all came from Coulomb's law. How do we do the same thing with electric potentials? And this is where I got a little weird with you in class today. I'm going to get weird again because I think this is a really good way to think about it. I want you to sort of mentally try to picture what's happening. So let's say I have a charge Q. I'm going to put it over here. And let's say it has an electric field that points outwards because it happens to be a positive charge. It could be a negative charge, but I'm just making it positive. It makes it a little simpler. Okay. And let's say I come out here. And I'm at some point P, that's a distance R away. I'm going to call it capital R away from the center of point Q. But I want to know how much potential energy would a little charge Q, small q, have were I to place it at point P. Right, I put it there, it has potential energy. I know it has potential energy because it would be hard to get there. It would have to push it in. And if I let go, it's going to go out. So I know it doesn't want to stay there. It has some potential energy. There's something going on. It's not going to stay in a certain spot. So one way I can think about that is if I take that charge, stick it in my back pocket, go all the way out here. And I can say, all right, I'm going to start really far away, infinitely far away, because I'm going to define infinity as my zero potential energy. I'm really far away. I'm coming in and I'm pushing that charge in and I'm pushing it in and I'm pushing it in and I'm pushing it in and I'm doing all this work and I'm plopping it down there. So I can define the potential energy that Q has relative to infinity as the work it took to get it from infinity to that point that I did. Well, now it has potential energy, right? Another way to think about it that turns out to be super helpful, it eliminates all kinds of confusion around signs and makes this a lot easier to picture, is now that that charge has potential energy, what's going to happen if I let it go? Well, the field is going to push it back out to infinity. And I can say, well, the field is going to do work on this charge. The field is going to take this charge Q and it's going to push it all the way back out to infinity. And really the work the field does to push it out to infinity is going to be the same as the work I do to push it from infinity there. I have to do work coming into this system as an external agent to push the charge in, but then the field is also going to do positive work because the force is pointing that way, the electric field is out, it's moving that way. The field is going to do positive work to push it out to infinity Because the electric field and the vector you're moving along point in the same direction, it's a little easier to think about the second case than the first case. So let's do that. Let's actually write that expression. So we're going to have our electric field, right? We have a force on this little charged cube. It's going to push it out to infinity. And I want to think about the fact that every step of the way, the force is changing. So every time I take a step, I have a new force. I've got to multiply them, stick it in my pocket. Take another step, I have a new force times distance, multiply it, add it to what's in my pocket. Take another step, I have a new force, multiply them, stick it in my pocket. That's what an integral is, right? You need to do the integral here because you have a force that's not constant over space. If it was constant, you could just multiply. It would be easy peasy. Okay, so let's define the potential V at point P to be the work that the field does on the charge to push it back out. Same as the work I did to push it in the first place. So that's going to be the integral from what am I saying? From R to infinity. Now, the force on this charge is going to be the electric field created by the source charge times Q, the little charge that's there, because force equals EQ. And then I'm going to dot that to dr, my little, incremental path that every step that I'm taking is pointing in the r hat direction. Now, E of r points in the r hat direction, dr, my little distance that I'm moving, points in the r hat direction. They both line up, the dot product is 1. That's why this is a nice way to think about it. Okay, so I can pull, first thing I can do is pull my Q out over to here. Oh, sorry, what did I just do? This is the potential energy at point P. The force times the distance is the potential energy. It's the work that the field did to push it out, which is the potential energy that the charge had at point P. Now I'm going to divide these two out. So U of P divided by Q equals the potential at point P. It's going to be the integral from R to infinity, E of R dr. Okay, let's think about what that is now. Okay, the potential at point B, which is the work done by the field per unit charge in moving a positive test charge out to infinity. It's the electric field is saying, hey, get out of here. And it's pushing this charge all the way out to infinity. The electric field is doing work. That work is coming from the potential energy that the charge had over here. I did work to get it there. It has potential energy. Now the field is going to push that charge out, and the potential energy it had at point P becomes the work done by the field in pushing it out. So I like writing it this way because it's really telling you what's going on. Potential energy that I have transforms into the work done by the field in pushing the charge all the way out to infinity. I'm going to write that over here. I'm going to erase this. The potential at a point P is equal to the integral from R to infinity, E of R dr. Okay, now remember that's relative to infinity. So you're going to see why I like this in a minute. Let's take a look. Let's do a quick example and get the potential near a point charge. That's a cute little example that we can do. So let's say I have a point charge Q, just like I did before. I have some point A over here, and I want to know what's the potential at point A. Well, using this equation, I know the potential at point A is going to be the integral from point A to infinity of the electric field produced by Q dot dr. So let's do that. Potential at point A is going to be the integral from, let's say A is a distance R away, R to infinity, from point A out to infinity, E of R, which I know is KQ over R squared, and I know that's in the r hat direction, dot dr. And then I can evaluate that integral. KQ over R squared is minus KQ over R. Evaluated from R to infinity, minus KQ over infinity is 0, minus KQ over R equals KQ over R. And that's the potential near a point charge. So I'm going to write that over here for a point charge. a distance r away from the point charge, the potential relative to infinity is going to be equal to k q over r at point P. Now, what's neat about this is you can sort of convince yourself, all right, what if the Q were negative? What would change here? Well, the electric field would be the same, but it would be in the opposite direction. It would be in the negative r hat direction. So when I did that product between dr and the electric field, I'd get a negative sign. And so I'd wind up with another negative over here, and that would give me a negative result. So the beauty of this is that it's a scalar quantity. If I put in the proper sign of Q, I get the right answer for the potential. So if I put in positive Q, because I have a positive source charge, that means it's going to create a positive potential up distance r away. If I have a negative source charge, I put in the negative Q, it's going to create a negative potential. It's more like a hole than a hill. Okay, this is an important equation, the potential near a point charge. Let's say I had a whole bunch of point charges. I want to know the potential in the middle. The beauty of this is not a vector. I can be like kq1 over r plus kq2 over r plus kq3 over r plus kq4 over r plus kq5 over r plus kq6 over r, and I just add them all up as numbers. Some could be positive, some could be negative. They could be all different q's and distances away. Doesn't matter. I can get the total potential at a point in space just by plugging it into that equation. All right, the reason why I want to do this, and let me get back to what I was saying. I'm going to keep this equation here because I like it. Let's say I'm interested in something slightly different. Actually, I'm going to erase it. Let's say I have a source charge Q. It doesn't have to be a source charge Q, but it's just easier to visualize. And let's say I have a point A, and then let's say I have a point B. And let's say I want to actually look at the I want to analyze the potential difference between A and B, right? Let's see if we can do that. The way I like to do that is I like to go back to this equation and think about what it really means. So let's make a graph. Let's make a graph of E of R versus R. And let's think about that for a minute. Like, what is this integral really calculating? Let's say this is my electric field, it just goes in some random direction. And let's say I'm starting here at point A. Well, I know the potential at point A is equal to the integral from A to infinity, E of R dr, right? I'm just going to do that integral, and that is this area here. All over here, this area. This lovely area all the way out to infinity. That is what I've just calculated, the area under this graph. Now let's say I had another point, point B, which is over here. And let's say I wanted to know what is the potential at point B? Well, it's just going to be the same integral, but instead of starting at A, we're going to start at B and go out there. So let's do that. The potential at B is going to be the integral from B to infinity, E of R dr. Well, that's good. So I know how much work the field would do per unit charge in moving a test charge from A out to infinity. I know how much work it would do from B to infinity. But, I know you see exactly what I'm going to do here, which is I'm really interested in the amount of work the field does in going from A to B. And since A is the bigger integral, you can kind of see if I just take this integral, the integral from A to infinity, and I subtract the integral from B to infinity. Can you see if I write below this? Oh, I think you can. Then you get the integral V of A minus V of B is just going to be the integral from A to B of E of R dr. That is the most important result of this whole thing. The amount of work the field does per unit charge in moving a charge from point A to point B is going to be just equal to the definite integral from A to B of the electric field over that distance. Okay, that's so important, I got to write it somewhere else. Where else can I write it? I'm going to write it up here because I'm going to erase all this business. So the potential at point A minus the potential at point B. Remember, this is a bigger area than this, so if I subtract, I get a positive number. That's going to be equal to the integral, now definite, from A to B of E of R dr. A lot of times in books, you're going to see this written in a different way. You're going to see this written flipped. VB minus VA equals negative the integral from A to B E of R dr. All that is a negative here and a negative here. But I think it destroys the intuition of what this really is. Because there, what it's saying is the potential difference, if you go from A to B, the potential difference V of B minus V of A is equal to negative the work done by the field in moving the charge from A to B. And I don't think it's necessary to be like the opposite of the potential difference is equal to the negative of the work done by the field in moving from A to B. You could just be like the potential, like the work done per unit charge by the field in moving from A to B is going to be equal to the potential of where it starts minus the potential of where it ends, because it started with more potential than it ended with. The change in the loss of potential that it had is going to go into the work done by the field in moving it from A to B. I think like there's no reason to flip these and have an extra negative sign. It just doesn't make any sense. So I don't know. I like it this way. If you want to write it the other way, you could do VB minus VA equals minus integral from A to B E of R dr. I don't really think it's helpful to do that because it really correlates to what's going on in this graph. Otherwise, you have negative areas and upside down graphs. It's just not as nice. Okay, let's do a different example with this. That's the most important equation because it's also a general case of this, right? Because when B is infinity, V at B be defined as 0. So it's the same thing. Let's look at an old familiar friend, the uniformly charged sphere of radius r. This is example 2. And the final example, because I know this is getting to be a long video. Okay, so there's radius r, it's a sphere. Let's say it has a total charge Q spread throughout its volume, right? And remember Q enclosed, remember we could write the electric field for R less than R. Make it a little interesting and not do the outside of R, but the inside of R. The electric field for R less than R is going to be given by, remember it was Q, just to review, it was the total charge divided by 4/3 pi R cubed times 4/3 pi R cubed, the little r of where you are, right? That's your Q enclosed divided by R squared times K. K Q enclosed over R squared. And when you did that out, you wind up with 4/3 pi R cubed, and then R squared. You get K Q R over R cubed was the electric field as a function of R inside a sphere. Just a little review, plus I never remember for some reason, I just have to redo it. Okay, so let's figure out, let's say point A is the center of the sphere and point B is the edge of the sphere. What's the potential difference between A and B? So that, what is the potential at A minus the potential at B? How much work does the field do in moving the charge from point A to point B? So let's do that. And let's just use this integral. So V at A minus V at B, I'm going to erase all my little business over here, is so I know my E of R here, I'm just going to write it out, is KQ, it's linear in R over R cubed, remember. And now I'm going to just do my integral. So V at A minus V at B, the potential difference between here and here, is going to be equal to the integral from A to B, which is the integral from 0 to R, right? That's my bounds of my integration, times K Q R over R cubed dr. And the electric field and the dr point in the same direction, so the dot product is again 1. KQ over big R cubed is just a constant, so I get V at A minus V at B equals that integral, which is equal to KQ over R cubed times R squared over 2 evaluated from 0 to R, and that V of A minus V at B is equal to KQ R squared over 2 R cubed, and I'm almost there, minus 0, and that equals KQ over 2 R. So that's the potential difference. That is how much the potential changes in moving from A to B. If I were to think about my little graph, it's the amount of area in between the potential at A and the potential at B. It's the integral from A to B of how much work the field does per unit charge to move a charge from point A to point B. So now what's cool about that is I know that potential, that's a potential drop, right? V at A minus V at B, this is a positive number. What that means is that V at A is going to be more than V at B. And that makes sense, right? Because of the definition of potential, which is that if I'm over here at A, the field's got to do all this work to push the charge out. It's got to start all the way at the middle and push the charge all the way out. And it's going to actually get interesting once we get outside the sphere, because the electric field actually changes form, becomes inverse square. So we'll have to do the integral in 2 different parts if we wanted to really look at this whole thing. But I have a V at A, I have a V at B, which is going to be the work it would take to push it from B all the way out to infinity, right? And so the potential difference, V at A minus V at B, A is more. The field has to do more work starting at A than it does at B. So it makes sense that V at A minus V at B would be positive. So now the field did that work. It gets over here, right? Now, like that's the difference. That's the change in potential. If I come along and I multiply that by Q, I can get the change in potential energy of the charge. If I know the charge lost potential energy, where did it go? And you know it went into kinetic energy. So I can take that amount we'll see of energy loss, and I can turn it into kinetic energy and figure out how fast the charge is moving by the time it gets over here. So that's a quick example of how you use this. This is like the really important equation, as well as the version of it when we're operating in infinity. And then there's the electric potential a distance r away from a point charge when we're calling the zero at infinity. That's enough for now. If you watch this whole video, good for you. And now you can go on and do some problems. All right, I'll see you later. Bye.